Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullah. Aujourd'hui, nous allons assister dans le cadre d'une soutenance de doctorat 3e cycle, filière génie civil, spécialité géotechnique, qui sera présentée par le doctorant Nouri Abdeslam, l'intitulé de la thèse, c'est valorisation des sols fins en matériaux de construction. Donc, je vous rappelle que le jury est composé de M. Sassad Salah, professeur à l'université 20 août 55 Skikda, et M. Woutel Jafatah, en tant qu'examinateur, MCA à l'université 8 mai 45, Guelma, et M. Nouri Mohamed Saleh, professeur à l'université 8 mai 45 en tant qu'encadreur, et donc on signale l'absence de Mme Bouchmida Salima en tant que co-encadreur, donc elle est absente. Et ce jury est présidé par moi-même, M. Rouili Ammar, professeur à l'université 8 mai 45, Guelma. Donc je vous invite à vous faire une brève présentation d'environ 35 à 40 minutes, dans laquelle vous allez exposer les principaux résultats obtenus dans votre recherche. Après, on va passer à la séance de questions-réponses. Espérons que vous respectez le temps alloué à cette présentation. À vous la parole et bon courage.
Merci, Monsieur le Président. Salam alaikum. Distinct Chairperson, esteemed committee's member, respected colleagues, and honored guests. Good morning. My name is Nouri Abdeslam, and today I will be sharing the key element of my research that is titled in French, La valorisation des sols fins en matériaux de construction. Over the past 5 years, I have dedicated myself to exploring this topic with the aim of contributing meaningful insight to our field. In the outline of my presentation, I will begin with an introduction to the topic and the problematic that my thesis aims to address. Next, we will explore the concept of raw earth construction and delve into the sources and application of BioBinder. Specifically, I will discuss two critical areas: raw earth construction, identification and utilization of biosource binding agent in enhancing the sustainability of construction materials. Section 3 will cover the soil test result. This part is crucial as it lays the groundwork for understanding the material's properties. We will discuss soil identification and soil verification according to the CAB standards, ensuring that the soil meets the necessary criteria for the use in compressed earth blocks. In section 4, we will focus on choosing the appropriate BioBinder. This section includes the selecting the best BioBinder, evaluation of different BioBinders to identify the most suitable one, procedure for extracting low-cost bean gum, a detailed explanation of how this particular BioBinder is sourced and prepared. The section 5 addresses the mechanical behavior and durability of CAB. This involves unconfined compressive strength, three-point frictional test, and durability test. In the final section of my presentation, we will cover the conclusion and perspectives. Let's start with the introduction and the main issue we're addressing. In Algeria, population growth in urban area is creating a strong demand for housing. A massive consumption of natural resources was necessary to cover all the needs. The use of concrete is accompanied by high CO2 emission from the production of cement. In Algeria, cement usage contributed to the production of nearly 11 tons of CO2, accounting for about 6.26% of the total emission of CO2. Raw earth construction is a serious candidate, especially the compressed earth bricks. The problem here is that the stabilization of the CAB is generally done with lime or cement. Also, the addition of hydraulic binders, cement or lime, has no relevance if we want to produce an eco-materials. So the question is, how can we replace these hydraulic binders? The main objective of this research is to use local materials to apply construction techniques using raw earth treated with an ecological binder that is more environmentally friendly. So, what is raw earth construction and where can binder be found? The raw earth is a building materials composed of a mixture of soil and water, which has been used since antiquity in various forms. It can be used in massive monolithic walls, based filling, a support of various nature, or in matched blocks. There are several techniques for construction building using raw earth, each with its unique procedure and application method. There are 5 commonly used techniques: daubed earth, poured earth, stacked earth, adobes, and compressed earth blocks. Waterland daub is an ancient construction technique that uses a woven lattice of wooden strips coated with a mud mixture. Advantages: flexible and can be used to create curved shapes, good isolation, and usually readily available materials. It can be used in traditional home, particularly in Europe and Asia, and for restoration of historic buildings. Ramed earth construction is a technique that involves compacting moist earth to form solid walls. The materials that we use: soil, usually with a good clay content, sometimes mixed with lime or other natural stabilizer. The advantages: durable, fire resistant, excellent thermal mass, and low environmental impact. It can be used in traditional and modern residential building, retaining walls, and various public structures. Cubs is a traditional building technique that uses a mixture of soil, sand, straw, and water to make different shapes, usually round balls, and then put it one on top of the other to make a wall. Advantages: excellent thermal mass, non-toxic materials, the ability to create organic shapes. It can be used in residential home, outbuildings, and architectic structures. Adobes construction involves creating sun-dried bricks from a mixture of clay and sometimes straw, which are then used to build structures. Advantages: good thermal mass, fire resistant, low cost, and environmentally friendly. It can be used in houses, communities, building, and various architectural sectors, and in arid and semi-arid regions. The final technique is compressed earth blocks, which we have used in this study. Compressed earth blocks are manufactured used a mechanical press to form uniform blocks from a mixture of soil and stabilizers. Materials: soil, stabilizers such as cement or lime, and water. The process for making compressed earth blocks: first step is to combine soil, stabilizer, and water to create a slightly moist monster. Compression: place the mixture into a block press and apply pressure to compact the soil into dense solid blocks. Curing: remove the blocks from the press and allow them to cure, which can be done either by air drain or, in some cases, in a controlled environment. Advantages: strong and uniform blocks, quick to produce, good thermal mass, and can be stabilized to increase durability. It can be used in residential and commercial buildings, boundary walls, and various construction projects. Now that we have explored various raw earth construction techniques, we'll discover the answer of the second part of the question. Where can binder be found? Natural organic polymers, biopolymers, can be divided into 4 main families of molecules. Polysaccharide. Polysaccharides are large complex carbohydrate composed of long chain of monosaccharide unit bounded. Second, lipids. Lipids are a large category of organic compounds that are insoluble in water but soluble in non-polymer solvent. They include fat, oils, wax, phospholipids, and steroids. Third, protein. Protein are a fundamental macromolecule composed of one or more long chain of amino acids. Finally, other complex molecules. These molecules, such as tannin found in plant tissue, have important proportion and play roles in plant defense, growth regulation, and historical human use like adhesive and varnish. There are several bio-sourced binders that are commonly used in all over the world in different fields, such as starch-based adhesive. It can be used in polywood production, particle board, and fiber board manufacturing, paper packaging. Casein-based adhesive. Casein-based adhesive are derived from casein, a protein found in milk. It can be used in wood bounding in restoration projects and stone marble repair. Tannin polyphenolic compounds from plants act as effective biobinder in industry, providing sustainable alternative to synthetic adhesive. It can be used in textile industry and leather tanning. Lignin is a natural polymer derived from plant materials, primarily from wood and agricultural residue. It can be used in wood composite materials and paper packaging. Having examined the potential of biobinders and discovered the different raw earth construction, it's extremely important to understand the properties of the soil we are working with. Soil testing is an essential step in determining the suitability of local earth for construction and ensuring the suitability and the durability of the structure we build. Let's take a look at the soil test result. First, the soil that we used in the study was obtained from a kaolin deposit in Bajarrah, located at 7 km west of city of Galma, next to Al Riyadh brick factory. This brick factory uses this material to produce baked clay bricks. The image on the right presents the 5 ponds that we have collected the soil from. This table presents the result of our soil identification test, covering key aspects such as grain size distribution, Atterberg limit, chemical properties, and compaction. Understanding these parameters is crucial for soil classification and assessing the suitability of the soil for raw earth construction and determining any necessary enhancement. After conducting a identification test, and according to the LCPC classification, the BD soil is clay sand. Beyond the basic soil properties, understanding the mineralogical composition is important for predicting the behavior and performance of soil in construction. This brings us to mineralogical identification performed by X-ray diffraction. Let's take a closer look at what the DRX test reveals to us. The mineralogical identification of the soil by X-ray diffraction test reveals the main constituent of the soil is quartz, a chemical composition associated with sand. Presence of iron oxide, known as malachite, in our study. Importantly, malachite does not adversely affect the biobinder used. Instead, it has beneficial properties that positively impact the soil. Therefore, its presence in our soil sample is seen as an advantage, highlighting its potential for mitigating environmental risks. The presence of aluminum silicate hydroxide associated with the mineral with clay mineral, particularly kaolinite. The alignment between the DRX result and the soil classification provide us with the confidence in consistency and reliability of our data, ensuring that we have a comprehensive understanding of the soil properties we are working with. After identifying the soil, it should be verified according to specific recommendation, granulometry, Atterberg limits, and compaction, before using it in manufacturing compressed earth blocks. The grain size distribution indicates the proportion of sand, silt, and clay in the soil. This information helps us to understand the soil texture and its potential behavior in construction. For example, a higher clay content can improve cohesiveness, while a balanced mix of sand and silt contributed to stability. On this slide, we have the granulometric curve of our soil beyond the recommendation range for the confection of the CAB for the compressed earth blocks. As we can see, the curve of the granulometric curve fit perfectly inside the recommendation range, ensuring that the materials is suitability for construction properties. Other bank limits, including the liquid limit, plastic limit, and plasticity index, provide us insight into the soil consistency and workability. These limits help determine the soil capacity to retain water and its plasticity, which are crucial factors in raw earth construction. On this slide, we have the combination of the liquid limit and the plasticity index plotted alongside with the recommendation range for compressed earth breaks. As you can see, the point fell well within the recommendation range. This means that the soil meets the limit at the Atterberg limit specification necessary for producing high quality CAB, ensuring that the material suitability for construction purpose. Compaction characteristics reveal the soil optimum moisture content and maximum dry density, which are essential for achieving the desired strength stability in constructed walls. As we can see, the combination for normal Proctor optimum moisture and moisture content and maximum dry density falls outside the recommendation range, indicating that this combination is not suitable for the production of the CAB. However, the combination of modified Proctor moisture content and maximum dry density fell within the recommendation range. By analyzing this soil test result, we can make informed decision about how the best utilize this local soil in raw earth construction projects. The soil verification according to the CAB standard has demonstrated that soil BD can be effectively chosen as primary materials for manufacturing compressed earth blocks. These findings confirm the suitability of the soil selection for the brick making process. Now that we have evaluated the essential characteristics of our soil for compressed earth blocks, let's shift our focus to selecting the appropriate view binder. The next section will explore how view binder can further improve performance and suitability of our construction materials. The choice of view binder was based on specific criteria: local production and consumption, estimated cost, and performance in improving soil strength. Carob Gap has emerged as the most suitable view binder among the options evaluated. Despite zero local consumption, Carob Gap can potentially be locally produced from approximately 4,000 tons of carob seeds at a rate of 0.5 tons per year. Economically, carob gum is moderately priced. Its incorporation into soil significantly enhances compressive strength, the highest among tested view binders. The superior performance in improving soil strength positions carob gum as an ideal candidate for view binding applications. Carob gum, also known as low-cast bean gum, is a food additive derived from the endosperm of carob seeds. It serves various purposes in the food industry, including as gelling agent, binder, adhesive, and thickener, and emulsifier. Additionally, carob seed find application in pharmaceutical and cosmetic industry. In this study, the carob gum used was extracted from carob seeds sourced from Bijaya. Following recommendation from a previous study, the biopolymer stabilizer content in this research was 1 and 2% of the dry soil mass. In this study, in our study, followed the detailed protocol by Dikia and all in 2008. The procedure for extracting low-cast bean gum is like migration of 100 gram of carob seeds in diluted sulfuric acid solution, 60 per 40 milliliters at temperature of 60 degrees for 60 minutes with regular agitation. Through rising and rubbing to remove the charred cocktail from the seeds. Overnight soaking of decorticated seeds in distilled water to facilitate swelling of the endosperm and manually separation from the germ. Washing of the endosperm followed by the drying at 105 degrees temperature for 4 to 5 hours to stabilize mass. Grinding of the dried endosperm to produce carob gum. Mechanical behavior and durabilities of the CAB. Before diving into the mechanical behavior and durability of our construction materials, let's begin with simple preparation. All tested specimens were compacted using the static compaction method with a uniform press at the speed of 20 mm per unit. Two types of specimen were prepared: cylindric specimen with a diameter of 77 mm and height of 154 mm for initial compression and durability test. Parallelepipedic specimen measuring 21.75 cm for multiply 14 multiply 9 cm for 3-point bending tension test. The specimen preparation protocol is: natural soil was dried and mixed with dew binders. Water at the optimal moisture content for the modified portor was added immediately. The mixture was weighted, placed into molds, and statically compacted into layer to achieve maximum dry density of 1.87 gram per centimeter cube. Specimens were demolded, sealed with thick plastic, and stored in climatic chamber at 22 degrees. Unconfined compressive strength test was carried according to French norm standards. The tests were conducted on untreated sample and sample treated with 1% and 2% carob gum, respectively. The compressive strength USCS is measured at several ages: 0, 7, 14, and 28 days. The image on the right represents the unconfined compressive strength for all the specimens with the minimum threshold recommended by the French norm. We observed that the unconfined compressive strength of untreated sample and 1% carob gum treated sample at 7 days and 14 days fell below the minimum threshold of 1.6 MPa recommended by the CAB standard. However, at 28 days of curing, the unconfined compressive strength of 1% carob gum treated sample and 2% carob gum treated sample exceed the threshold, demonstrating that the suitability of construction purpose according to the CAB norms. The main factor affecting the average of the unconfined compressive strength can be demonstrated by the photo on the right. The curing time effect, the average strength increase from day 0 to 14 with diminishing effect after day 14. Carob gum dried into a rubby or glassy state, binding particles and increasing strength. Binding dosage effect, strength increase with higher dosage, 1.6 MPa at 28 days for 1% carob gum, 2.2 MPa at 28 days for 2% carob gums. Hydrogel in soil voids acts as binding agent, creating a strong soil carob gum matrix, a better bearing capacity. 3-point frictional test. Frictional tensile strength increased from 0.2 MPa to 0.41 MPa after 28 days with 2% carob gum, significantly strengthening compressed earth breaks during curing. Tensile strength decreased compared to unconfined compressed due to the easier crack propagation under tension. Higher dew binder content correlate with increased tensile strength, emphasizing its impact on material strength. We arrived to the durability of the CAB. Drip test was carried according to the following standards. Origin of death is measured for several age cured samples 0, 7, and 28 days. The depth of erosion is measured every 15 minutes. Erosion test and treated specimen and 1% color gum stabilized specimen at 7 days and more are prone to erosion. Specimen with less than 5 mm erosion depth are classified as slightly erodible. The conclusion that we can conclude that the addition of biopolymers significantly improve the erosion resistance of earthen materials. The dip test was carried according to the following standard. Loss of mass is measured for several ages, cured sample 0 and 28 days. The untreated samples given a soil loss mass of nearly 13%, and it can be classified in class 2, while 1 and 2% color gum treated samples has given 2 and 1.5 soil loss mass respectively and can be classified in class 1. According to the classification, the untreated sample can be used only in internal wall, while color gum treated sample can be used in external wall, exposed to natural weathering and coated external walls. We arrive to the end of the presentation. The last section is conclusion and perspective about our work. This research aimed to evaluate the influence of biological methods on the properties of compressed earth blocks stabilized with color gum, namely mechanical behavior and durability. The following main conclusion can be drawn from this study. The biopolymer studied here is color gum. It has a significantly positive impact on the mechanical properties of the CAB. It was observed that the unconfined compressive strength of the soil is improved within the addition of the biopolymer. This addition led us to an increase in strength with a curing time for both percentages of color gum treated soil. The biopolymer stabilized earthen materials has a satisfactory durability performance against water-induced deterioration. The addition of color gum has reduced the rate of erosion in the drip test for both percentages 1 and 2%. The soil loss was significantly reduced the dip test by adding the color gum. This solved the problem of water erosion of unstabilized CAB. By increasing curing time from 1 to 14 days, the unconfined compressive strength and durability of the CAB were increased substantially. Untreated soil BD and 1% color gum at 7 days, both erodibility index of 3 and depth of erosion around 9 and 6 mm respectively, can be used only in arid area. 1% color gum at 28 days and 2% color gum at 7 days and 2% color gum at 28 days, all with erodibility index of 2 and depth erosion around 4.5 mm, 5 mm and 3 mm respectively. It can be used in both in semi-arid and arid area. According to the classification of compressed earth blocks, an amended soil with 30% mass loss is suitable for class 2 and can be used in internal walls. 1% colored gum with nearly 2.5% mass loss and 2% colored gum with nearly 1.5% mass loss are suitable for class 1 and can be used in external walls and coated exteriors. This study demonstrates a promising alternative to more environmentally friendly stabilizer used in earthen construction materials. Evaluate the impact of bio-based binder on the hydrothermal properties of compressed earth blocks, assessing their response to temperature and humidity fluctuation to optimize thermal performance and moisture resistance. Investigate the potential application of this technology in diverse contexts, such as rural area and disaster-prone regions, aiming to provide affordable and suitable housing solution. Study the long-term effect of drying and wetting cycle on stabilized earth breaks to assess their durability over extended periods. Investigate the effect of blending different view-based binders such as carob gum, xanthan gum, and guar gum to tailor formulation for specific construction needs. Explore the addition of various types of fibers to enhance the frictional strength of the CIB, thereby strengthening the structure and expanding their application potential. Thank you for your attention, and now I'm open to any questions and look forward to discussing my research